Hello viewers, welcome to our YouTube channel Incredible Maths. In this video, we will solve a problem asked in February 2022. This problem belongs to part B. The problem is, let a matrix M is given in which 1 is an eigenvalue of M. So we have to check which of the following given statement is true. So the first option -2 is an eigenvalue of M, second option 3 is an eigenvalue of M, third option eigenspace of each eigenvalue has dimension 1, and option D, M is diagonalism. So given that 1 is an eigenvalue, so from this we can find other two eigenvalues using the properties of trace and determinant of the matrix. Now, since 1 is an eigenvalue, so we know that sum of the eigenvalues by the properties, sum of the eigenvalues of M is equal to trace of M. So this implies, so let lambda 1, lambda 2, lambda 3 be the eigenvalues. Since it is a 3 by 3 matrix, so there will be 3 eigenvalues. Let us denote the 3 eigenvalues by lambda 1, lambda 2, lambda 3. So sum of the eigenvalues lambda 1 plus lambda 2 plus lambda 3 is equal to trace of the matrix. Trace of the matrix is nothing but sum of the diagonal entries. So sum of the diagonal entries 0, 2 plus 2 plus 3. So 0 plus 2 plus 3. So also we know that 1 is an eigenvalue. So let us take this lambda 1 as 1. So 1 plus lambda 2 plus lambda 3 equal to 5. So this implies lambda 2 plus lambda 3 equal to 4. Next, using the property of determinant of eigenvalues, so the next property, product of eigenvalues of M, so this is equal to determinant of M. So product of eigenvalues lambda 1, lambda 2, lambda 3 is equal to determinant of M. So from the given matrix we can find the determinant. So determinant, so when we expand along the first row, so we'll have the determinant is, so minus plus minus plus, so minus of minus 1 into 3 plus 1. So the answer is 4. So determinant is 4. Also lambda 1 equal to 1. So this implies 1 into lambda 2 into lambda 3 equal to 4. So we will get lambda 2 into lambda 3 equal to 4. So we have two equations and two variables. So from this we can find lambda 2 and lambda 3. So sum of lambda 2 and lambda 3 is 4, and the product of lambda 2 and lambda 3 is 4. So therefore, so by solving these two, so we will get okay, so we will form the equation x square minus sum of the roots. Sum of the root is 4, so we get 4x plus product of the root is 4 equal to 0. So we get x minus 2 square is equal to 0. So we will get x is equal to 2 comma 2. So these are the roots. Therefore, eigenvalues of M are, so already given 1 is the eigenvalue, other two eigenvalues are 2 comma 2, so repeated eigenvalues. So from these two, from the eigenvalues, so we can eliminate the option A and B. So here minus 2 is not an eigenvalue of M, so this is false, and similarly 3 is also not an eigenvalue of M, so this is false. So now we will check which of the options C and D is true. So to check whether C is true, we have to find the eigenspace of each eigenvalue. So that is, so we have to find eigenspace for each of the eigenvalues. So let us take lambda is equal to 1. So we will first consider the eigenvalue lambda equal to 1. So next we have to solve the equation Ax we have to solve the equation a minus lambda I times x is equal to 0. So from this we can find the eigenspace corresponding to the eigenvalue 1. So here matrix A is M. So A minus lambda I, so lambda is equal to 1, so we'll get so minus 1, 0, 1, so 2 minus 1 will be 1 and minus 1, and here 1, 1 and 3 minus 1 will be 2. x1, x2, x3, so let us take the unknowns as this one. So now we can solve this system using Gauss elimination method. Okay, so we will take this one, the matrix minus 1, so minus 1, 0, 1, 1, minus 1, 1, 1, 2. So we apply elementary row operation, so to get 1, 1, multiplying the first row by minus 1, so we get 1, 1, 0, and this one, so when we add these two, so we get 0, 0, minus 1, and similarly here 0, 0, 2. So this is equivalent to 1, 1, 0, 0, 0, 1, and here 0, 0, 0. So therefore, so from this the equations are x1 plus x2 equal to 0 and x3 equal to 0. So therefore there is one free variable. So the leading variables are x1 and x3 are leading variables, and x2 is a free variable. Therefore we will assign parameter for the leading variable, for the free variable s. So therefore the solution x1, x2, x3 so this is equal to, so x1 equal to minus x2, so this is minus s, x2 is s, and x3 is 0. So since there is only one parameter, so here, so this implies eigenspace corresponding to eigenvalue lambda equal to 1. So here we need to find dimension. So dimension is number of elements in the basis. So number of elements in the basis correspond to the number of parameters. So this dimension is 1. So next we have to check for lambda equal to 2. So that means we have to solve the equation a minus lambda I into x equal to 0. So here lambda equal to 2. So therefore ai minus lambda I equation is okay. So minus 2, minus 1, 0, 1, 0, minus 1, 1, 1, 1. So this into x1, x2, x3 equal to 0. Second we will take the coefficient matrix and apply elementary row operation. So this is equivalent to 2 minus 1, 0, 0, minus 1, minus 2. So here 0, 1 and 2. So 2 minus 1, 0, 0, 1, 2. So it is 0, 0, 0. So here also there is only one 0 row. So it means here these are the again this is equal to 1 minus 1 by 2, 0, 0, 1, 2, 0, 0, 1, so 0, So here this one x1 and x2 are leading variable, so x3 is the free variable. So therefore x3 equal to some s. Now we will form the equation from the reduced matrix, that is this matrix x1. So this one is x1 minus of x2 equal to 0, and the second equation is x2 plus 2x3 equal to 0. So x3 equal to s, so x2 equal to minus 2 x3, so minus 2s, and x1 equal to, so 1 by 2 x2, so x2 is minus 2s, so therefore x1 equal to minus s. So the solution x1, x2, x3 equal to x1 is minus s, x2 is minus 2s, and this one is 0. So this one is not 0, this one is yes. Okay. So from this x3 equal to s, x2 equal to minus 2s, and x1 equal to yes. Okay. So here we have only one parameter, so this implies dimension of eigenspace corresponding to lambda equal to 2 is 1. Okay. So here for the matrix M there are two eigenvalues. Okay, so we have seen already the dimension of eigenspace corresponding to the eigenvalue lambda equal to 1 is 1, and here also it is 1. Therefore each eigenvalue of matrix M that is eigenspace of each eigenvalue has dimension 1, so this is true. Okay, and the next option, the fourth option will be wrong. So diagonalizable means, so the definition, algebraic multiplicity is equal to geometric multiplicity for each eigenvalue. For lambda equal to 1, algebraic multiplicity is 1 and geometric multiplicity is 1, and for lambda equal to 2, algebraic multiplicity is 2. So for lambda equal to 2, algebraic multiplicity is 2. For lambda equal to 2, algebraic multiplicity is 2 because it is repeated twice. For lambda equal to 2, geometric multiplicity is 1. So this is according to the dimension of eigenspace. So since dimension of eigenspace for lambda 2 equal to 2 is 1. So here algebraic multiplicity is not equal to geometric multiplicity, therefore the matrix cannot be diagonalizable. So diagonalizable means algebraic multiplicity should be equal to geometric multiplicity for all eigenvalues. So therefore the option D is wrong. So the only correct option is option C. If you are interested in content of this video, kindly like and share with your friends. Also subscribe for latest videos. Thank you.